Let's head over to Notebook 11A, which is a random forest in H2O. You've got this, there are no to-dos, we'll just click through it together. At the very top you can see, rather than taking our linear model estimator or whatever it was, we're now taking the H2O random forest estimator. We're still bringing in the grid search. I'm not sure that I use it in this script. We're going to read in the data, as usual, the variables, set train validation and test, and here we go. Let's initialize H2O. H2O is ready to roll. Push the data to our Java virtual machine, set up some indices for train and val. Now let's look at the parameters. I've copied the help for some of these parameters from H2O so we can just see what they are. We talked about entries. I've set that to 200. Maximum depth of each tree on the AMIS data, 20. Is that optimal? Is that enough? I don't know, but it's a good starting point. Row sample rate per tree from 0 to 1. If you remember, bootstrapping would give you a representation from 63% of your houses, although some houses will be represented twice. And what we do here, we choose a proportion of the rows to make it into each individual tree, but there will still be different rows coming into each different tree, and so the trees will be decorrelated. Column sample rate per tree, that is a hyperparameter to introduce more randomness between the trees. We've set it at 0.9. Now, mtries. Mtries is actually a big part of random forest, and I'd totally forgotten to mention it. Well, I hadn't totally forgotten to mention it because I'd mentioned that we subsample at random the columns that come into each tree. But once we've done that, the columns that we try at each split are selected at random, and only a few columns are selected. The default is that for classification, it's the square root of p, where p is the number of columns, and it's p over 3 for regression. We're doing regression. We've got about 70 columns, and that would mean there's something like 23 columns are chosen at random at each split. And it's only within those 23 columns that we will find the best split. Min rows we've talked about. It is very important to set a seed, especially in your assignments. And the stopping metric is MAE. Sorry, we didn't talk about stopping metrics. H2O allows you to set a stopping metric, which means that your trees don't carry on building themselves tree after tree after tree if the mean absolute error is not improving. In order to decide when to stop, we have to tell it what to measure. We'll measure MAE, and we have to tell it that it should try building another 20 trees at any one time, and it's only if 20 trees haven't improved the MAE, then we should stop. If we're doing this, obviously we need to give it a validation frame on which to try stopping, because it would never stop based on training, because almost always training error is going to improve. So those are some of the parameters. I strongly recommend you look up the help. Here we're going to unpack the parameters. We've discussed this previously. And finally build our random forest. That is done. Incidentally, you notice that model.train is exactly the same as we had with the H2O generalized linear model estimator. So this API is very consistent. By the time you've instantiated a model by doing model equals whatever it is, the rest of the process is always the same, model.train, and here we go, model.predict. I am puzzled why the predictions came out different to this script when I ran it last year. I have a feeling I might be running it on slightly different data, but it is certainly not reproducible, so I would get 0 marks for this. Now, how can we know if we've built enough trees? What we can do is that we can take one tree and measure the train and validation error. Then we can take 2 trees, average them, measure the train and validation, take the first 3 trees. So in order that they were built, just take the trees and for it sequentially, every time we have a new tree, find the train and validation error. And what we should find is once we've added an optimal number of trees, the validation error has reduced as far as it's going to reduce, and from then onwards it's flat. Conveniently, the model trained by H2O has an attribute called scoring history, And from scoring history, we can get the number of trees, which will just be increasing from 1 to 200. And for each number of trees, the validation MAE that you arrive at by averaging all the number of trees up until that point. Here we have it. Here is the validation curve in red. It does seem to be going down pretty much all the way through the range. Probably more than 40 trees is not really necessary. Now, it doesn't hurt to grow a large number of trees, but if you're using a large data set, it can just simply take a long time to grow a large number of trees. So it's worth knowing roughly how many trees you should bother building. I tend to build one model with a large number of trees, have a look at when validation flattens out, and then hope that that flattening out will be repeated if I now try different hyperparameters. Grid search. The sample rate, which is the proportion of rows which are selected for growing each tree, the col sample rate per tree, which is the number of columns, and the minimum number of rows before splitting a leaf. Those three things it seems reasonable to try to tune. If we try 5 of each of these, we will have 125 forests to grow, which will take a while. So we're actually only going to grow 10 random forests. We're going to randomly select from our grid which random forest to grow, and I strongly recommend this paper where you'll see the effectiveness of a random grid search. For some reason, I have programmed this up myself rather than simply using random grid search in H2O. For your work, incidentally, I strongly recommend you do use their random grid search. It should work. I'm just setting up a data frame. You can see I've got all the possible combinations of those 3 variables. I have 180 rows. Why? Let me see, 1, 2, 3, 4, 5, 6 possibilities for sample rate, 5 possibility for min rows, that makes 30, and then 6 times 30 because I've got 6 column samples per tree, so that makes sense. Shuffle the data frame, and right. Well, I'm not going to grow 180 models. Like I said, I will grow a certain number at random. Let's make it 20. I've written here H2O's random grid search would be better since it will parallelize over available cores, and at some point in your project, but being very careful with your budget of remaining free credits, you probably do want to spin up a machine which has more than just one core, just so you can benefit from the reduced training time in your final assignment. That took a little while to run. Let's see the best performance. 14983 is not bad, but it's not brilliant. I've got a little bit of code over here which tries to look at how quickly the random grid search gets close to the best model that it found. What you can see over here, that we've searched about 10% of the grid, and within what we searched, we found the best model, or something as good as the best model, after searching 8% of the grid. If you run this for all 180 models in the grid, it's quite interesting to see that after searching only maybe 20 models, you'll find something very close to the best. It kind of demonstrates that random grid search is a pretty sensible thing to do. There's more code here to show what would happen if we searched in a different order. I think this piece of code only works if you've actually searched the whole grid, which I haven't right at the moment. Here I'm just dropping rows that we haven't searched. Finally, let's find a little bit of detail about this best model. Sample rate 1, that's quite interesting. I don't really like that result. Col sample rate per tree 0.9. Min rows 2. None of this looks like stuff that I really like. I would have wanted to see a higher min rows and a lower sample rate. I'm kind of surprised. I might be tempted, just for the sake of it, to run all 180 models in the grid. Interesting. Look at this overfitting in this model. It's just insane. And I seem to have spotted that last year when I did this. I've written to myself a note. I'm not prepared to use the best model because the overfitting is crazy. Instead, I'm going to limit myself to the best model which does not have dreadful overfitting. So I'm only going to allow myself to choose models which have an overfitting of less than 3,000. That's much better. I'm much happier with this model. Sample rate right down, close to the baggings. Sample rate, min rows right up, which makes sense because even the individual trees don't have to be insanely overfitted. It's not always going to help. Random forest with the chosen hyperparameters, max depth 20, apparently sample rate is 0.7. Call sample rate per tree 0.2, min rows 20. That should do the trick. Failed. Okay, when that failed, I looked carefully at the error message and it said that the Java virtual machine had run out of memory. I'm not quite sure why it did that. Had I been using its own grid search, I could kind of understand because it stores each separate model in the grid, so it's going to start getting quite full. But all I did was I shut down H2O, I restarted it, and then I only uploaded into the Java virtual machine exactly the data that I needed to reach this point. Here we have a final model, train error 15843, validation 168, and test 169. At least it's not massively overfitted, but the result is pretty bad. What we can do though is create one final model of a train and val and see how that performs on test. At this stage I'm puzzled, looking at the output I have from this year where my test error is 16948 versus last year where my test error is 14801. I have a feeling it might be because I didn't search through the whole grid, which is kind of surprising given that I was saying you don't need to search through the whole grid, but because I'm curious, I am going to just pause the video and look a little bit more carefully. I ran a few more trees, did a bit of a bigger grid search, but I'm still not getting the same results that I had previously. That's not very good, but it's time to move on and look at gradient boosting models, so I'm going to leave it like this. And maybe we can just summarize. We started off with decision trees. We found that decision trees were low bias, but potentially very high variance. And if we tried to get the variance down by making the decision trees simpler, our performance suffered. Random forests are an inspired way to keep the low bias of decision trees, but also reduce the variance. And we've seen how they work. We inject randomness into each tree that we build so that the tree's predictions are not totally correlated. We try to do this in such a way that each tree remains relatively low bias, but the noise in the trees means that the variance in each individual tree gets cancelled out when we take the average over a lot of trees. We saw some of the ways that we can create this useful noise, the difference between the trees, by subsampling the columns, by subsampling the features, and there are one or two other ways that we haven't discussed. I do recommend that you look at all the parameters available to you in the H2O framework. That's it for random forests. We're going to move on now to gradient boosting.